This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. There's really not a lot more I can say about source conversion other than this. Pause the lecture and take a shot at converting these sources to their other-world equivalents. If it's a voltage source in series with a fixed resistance, swap it out for an equivalent current source in parallel with a fixed resistance. On the other hand, if it's a current source in parallel with a fixed resistance, change it to an equivalent voltage source in series with a fixed resistance. Ensure equivalency is maintained by solving for voltage across and current through the load in both configurations. Let's say for the first circuit, the load resistor is 500 ohms. Let's say for the second circuit, the load resistor is 800 ohms. Ideally, both configurations will induce the same voltage drop and current through the given load resistance. Again, make sure polarity is accounted for such that either source configuration induces current through the load resistance in the same direction. If you're tracking, you should have obtained the following results. Our first illustrated example features a 70 mA current source in parallel with a 190 ohm resistor in parallel with a variable load resistor. With a variable load resistance removed, an application of Ohm's law demonstrates the open circuit voltage will be 13.3 volts. Therefore, a 13.3 volt voltage source in series with a fixed 190 ohm resistor should behave identically to our original configuration. As proof of this equivalency, our original configuration is a perfect setup for the DC current divider rule. With the load resistor set at 500 ohms, we know incoming current, and we know both resistances in a parallel combination of two elements. An application of the DC current divider rule demonstrates current through the variable load resistor set at 500 ohms will be 19.3 milliamperes. A subsequent application of Ohm's law demonstrates voltage across the variable load resistor will be 9.6 volts. A modified configuration is a perfect setup for the DC voltage divider rule. With the load resistor set at 500 ohms, we know applied voltage and we know both resistances in a series combination of two elements. An application of the DC voltage divider rule demonstrates voltage across the variable load resistor will be 9.6 volts. A subsequent application of Ohm's law demonstrates current through the variable load resistor will be 19.3 milliamperes. Our second illustrated example features a 48 volt source in series with a fixed 250 ohm resistor in series with a variable load resistor. With a variable load resistor removed and a short circuit put in its place, an application of Ohm's law demonstrates the short circuit current will be 192 milliamperes. Therefore, a 192 milliampere current source in parallel with a fixed 250 ohm resistor should behave identically. As proof of this equivalency, with the load resistor set at 800 ohms, our original configuration is a perfect setup for the DC voltage divider rule. We know applied voltage and we know both resistances in a series combination of two elements. An application of the DC voltage divider rule demonstrates voltage across the variable load resistor set at 800 ohms is 36.6 volts. A subsequent application of DC Ohm's law demonstrates current through the variable load resistor will be 45.7 milliamperes. Our modified configuration is a perfect setup for the DC current divider rule. We know incoming current, we know both resistances in a parallel combination of two elements. An application of the DC current divider rule demonstrates current through the variable load resistor will be 45.7 milliamperes. Subsequent application of Ohm's law demonstrates voltage across the variable load resistor will be 36.6 volts. I've got a reasonable degree of confidence our answers are correct. Alright, that's about it for now. We'll make use of source conversion in later circuit analysis scenarios. It's a simple and effective means of making circuits easier to visualize and analyze. If you overwhelmingly prefer the voltage divider rule to the current divider rule, or vice versa, you have my permission to do a source conversion and make it happen using whichever techniques you prefer. Either configuration should yield identical results. In conclusion, this lecture presented circuit analysis technique known as source conversion. Source conversion allows a degree of flexibility in circuit analysis scenarios and allows one to employ certain circuit analysis methods in preference to others. Remember to review this material as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.